How large is the universe? Tonight, we're going to explore a question that will completely transform how you see reality itself. You've probably heard the term Milky Way thousands of times. You know it's our galaxy, this massive collection of stars spinning through space. But here's what most people don't realize. Our entire galaxy, all 400 billion stars, all 100,000 light years of it, is so impossibly small compared to the universe that it essentially disappears. It gets erased from significance. By the end of this journey, you're going to understand exactly why Carl Sagan said we live on a pale blue dot, and you'll see that even our galaxy is just another dot in an ocean so vast it defies comprehension. Before we dive in, if you enjoy these kinds of mind-bending explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Beautiful. When you look up on a perfectly clear, dark night, far from city lights, far from the glow of civilization, your eyes can distinguish approximately 6,000 individual points of light scattered across the cosmic darkness. Each one of those tiny pinpricks is a real star burning in the vast emptiness of space. Some of them are hundreds of times larger than our sun, nuclear furnaces so massive that our entire solar system could fit comfortably inside them. But here's what's remarkable about human vision. Those 6,000 stars represent just the tiniest fraction of what's actually there. When Galileo first pointed his simple telescope at the night sky in 1609, he discovered something that shook the foundations of human understanding. Where his naked eyes saw only empty blackness between the stars, his telescope revealed millions upon millions of additional stars, layer after layer of them, stretching away into depths that seemed to have no end. Think about that for a moment. In every patch of darkness you see between the familiar constellations, there are countless stars waiting to be revealed. It's as if you've been looking at a distant forest and seeing only the trees in the very front row, completely unaware of the vast woodland stretching away behind them. Now, let me help you understand just how far away these stars actually are. The closest star to us, beyond our own sun, is a small red dwarf called Proxima Centauri. It sits at a distance of approximately 4 2/10 light years from Earth. A light year, that's the distance light travels in 1 year, racing through space at an almost incomprehensible speed of about 5.8 trillion miles every single year. To put this in perspective that your mind can actually grasp, imagine you could travel at the speed of a commercial airliner, cruising along at a steady 550 miles per hour. If you pointed your airplane toward Proxima Centauri and flew without stopping, without slowing down, without ever landing, it would take you over 5 million years to complete that journey. 5 million years. That's longer than humans have existed as a species. Our most distant human-made object, Voyager 1, has been racing away from Earth since 1977. It's now traveling at about 38,000 miles per hour through interstellar space, faster than any human-built object has ever moved. And yet, even at that incredible speed, Voyager 1 would need 73,000 years just to reach our nearest stellar neighbor. 73,000 years. That's more than 3 times longer than all of recorded human history. But here's where this journey becomes truly extraordinary. All of these stars that you can see with your naked eye, every single point of light scattered across the night sky, they all belong to a single, enormous structure. They're all part of our cosmic home, a vast island of stars called the Milky Way galaxy, our galaxy. Let me help you visualize what this actually means. The Milky Way contains somewhere between 200 and 400 billion individual stars. 200 to 400 billion. If you started counting these stars right now, one star every second, without stopping to eat or sleep, it would take you at least 6,300 years to count them all. That's longer than the entire span of recorded human civilization. Picture this galaxy as a vast spiral, like a cosmic pinwheel slowly rotating in the darkness of space. It stretches approximately 62,000 miles across its main luminous disk, a distance so vast that light itself, traveling at 5.8 trillion miles per year, needs 100,000 years to journey from one edge to the other. And where do we live in this cosmic metropolis? Our solar system sits about 16,000 light-years from the galactic center, out in what astronomers sometimes call the galactic suburbs. We're not in the crowded downtown district where stars are packed tightly together, nor are we in the sparse outer regions where stars become lonely and isolated. We occupy a comfortable middle distance, in a region where stars are spaced just right for life to emerge and thrive. Our entire solar system, the Sun, Earth, all the planets, everything we've ever known, orbits around the center of the galaxy at a speed of about 155 miles per second. 155 miles every single second. We're all passengers on a cosmic carousel, spinning through space faster than you can imagine. And yet the galaxy is so enormous that it takes us approximately 200 million years to complete just one orbit. Astronomers call this a galactic year. Since our sun first ignited about 4.5 billion years ago, we've completed only about 22 trips around the galactic center, 22 galactic years. When dinosaurs roamed the Earth, we were on the opposite side of the galaxy from where we are today. When the first simple life forms appeared in Earth's oceans, we were in an entirely different galactic neighborhood. At the very heart of our galaxy, hidden behind vast clouds of gas and dust, lies something that would have seemed like pure science fiction just a few decades ago. A supermassive black hole called Sagittarius A star. This cosmic monster contains the mass of about 4.1 million suns, all compressed into a region smaller than the orbit of Mercury. 4.1 million suns, squeezed into a space so small that light itself cannot escape once it crosses the boundary. But our galaxy is far more complex than just a simple disk of stars. It's actually structured in 4 main components, each with its own character and story. There's the central bulge, where older, redder stars crowd together in the galaxy's downtown district. There's the flat disk where we live, organized into 4 magnificent spiral arms where young blue stars are continuously born. There's the spherical halo that surrounds everything, containing ancient globular clusters, dense balls of stars that are among the oldest objects in the universe. And pervading it all, there's the mysterious dark matter that we cannot see, but whose gravity holds everything together. Our solar system resides in what's called the Orion Arm, a relatively minor spiral feature nestled between 2 major arms, the Perseus Arm and the Sagittarius Arm. We live in a cosmic suburb, in a minor branch of the galactic spiral structure, orbiting an ordinary yellow star among billions of others. The spiral arms themselves are regions where stars are born. As clouds of gas and dust sweep through these cosmic compression zones, they collapse under their own gravity and ignite into new stars. The brilliant blue giants that outline the spiral pattern live fast and die young, burning through their nuclear fuel in just millions of years before exploding as supernovas. It's this constant cycle of birth and death that keeps the spiral arms bright and visible, even as the galaxy rotates and evolves. Surrounding our galactic disk in a vast spherical halo orbit hundreds of globular clusters, ancient cities of stars that formed when the universe was young. Each cluster contains between 100,000 and 1 million stars, all born at roughly the same time, all aging together in a compact sphere just 30 to 100 light-years across. These clusters are like cosmic time capsules, preserving stars from the early universe that are more than twice as old as our solar system. But perhaps the most mysterious component of our galaxy is something we cannot see at all. Dark matter makes up about 90% of the Milky Way's total mass, yet it neither emits nor absorbs light. We know it's there only because of its gravitational effects, like an invisible web that holds the galaxy together and prevents it from flying apart as it rotates. Without dark matter, the outer regions of the galaxy would spin so fast that all the stars would be flung into intergalactic space, leaving behind only an empty void where our cosmic home once existed. The Milky Way isn't alone in its cosmic neighborhood. Several smaller galaxies orbit around us like satellites, the largest being the Large Magellanic Cloud, which contains about 6 billion times the mass of our Sun and sits approximately 160,000 light-years away. These satellite galaxies are slowly being torn apart by our galaxy's gravity, their stars gradually joining the Milky Way in a process that has been going on for billions of years. Hidden throughout our galaxy are the remnants of stellar death. More than 1 billion neutron stars, the ultra-dense cores left behind when massive stars explode as supernovas. A typical neutron star contains the mass of our entire Sun, compressed into a sphere only about 12 miles across. The matter is so dense that a single teaspoon would weigh approximately 6 billion tons on Earth. More than the weight of Mount Everest, compressed into the volume of a teaspoon. And scattered throughout the galactic disk are millions of black holes, most containing the mass of dozens of suns. Yet despite their fearsome reputation, only a few dozen of these stellar mass black holes have been identified so far. They lurk invisibly in the darkness between the stars, detectable only when they happen to steal material from a nearby companion star, causing the stolen matter to spiral inward and heat up until it glows brilliantly in X-rays. Human behavior, until just over a century ago, humans believed that the Milky Way was the entire universe. Everything that existed, they thought, was contained within our galaxy's boundaries. The idea that there might be other island universes beyond our own seemed as fantastical as fairy tales, but our galaxy harbors violence as well as beauty. Deep in the galactic center, powerful gravitational forces occasionally fling stars out into space at incredible velocities, over 310,000 miles per hour. These hypervelocity stars become cosmic bullets racing away from the galaxy so fast that they completely escape our gravitational pull and head out into the emptiness between galaxies. Imagine a star, an entire nuclear furnace larger than our Sun, being ejected from its galactic home and condemned to wander alone through the cosmic void for billions of years. This violence serves a purpose, though. When massive stars reach the end of their lives, they explode as supernovas, stellar detonations so powerful that a single explosion releases energy equivalent to 10 billion hydrogen bombs every second for months on end. These cosmic catastrophes tear the star apart, hurling its enriched material across thousands of light-years of space. And it's this stellar violence that makes your existence possible. You see, the iron flowing through your blood right now, the calcium that strengthens your bones, the oxygen you're breathing at this very moment, none of these elements existed when the universe began. They were forged in the nuclear furnaces of ancient stars that lived and died billions of years before our Sun was even born. When those massive stars exploded as supernovas, they scattered these precious elements across space, seeding the cosmos with the raw materials needed for planets and life. Carl Sagan captured this profound connection when he said we are literally made of star stuff. Every atom in your body, except for hydrogen, was manufactured inside a star and delivered to this location by stellar death. You are not just living in the universe. You are a temporary arrangement of the universe itself, a way for 13.8 billion years of cosmic evolution to know itself. This understanding came to us only recently in cosmic terms. Until 1920, the finest minds in astronomy believed that our Milky Way galaxy was all there was. They thought the fuzzy spiral nebulae visible through telescopes were merely clouds of gas within our own galactic boundaries. The idea that these might be separate galaxies, each containing billions of stars, seemed impossible. Then came Edwin Hubble, working with the 100-inch telescope at Mount Wilson Observatory. In 1924, Hubble made a discovery that instantly expanded the known universe by a factor of millions. He identified individual stars within the Andromeda Nebula, stars that pulsed with regular periods, growing bright and dim in predictable cycles. These were Cepheid variable stars, and they served as cosmic lighthouses. Cepheids are remarkable stellar beacons. The brighter the star's intrinsic luminosity, the longer it takes to complete one cycle of brightening and dimming. By timing these pulsations, astronomers could determine how bright the star actually was. And by comparing this true brightness with how bright it appeared from Earth, they could calculate exactly how far away it had to be. When Hubble measured the distance to the Cepheids in Andromeda, he got a result that shocked the scientific world. The nebula was over 2 million light-years away, far beyond the boundaries of our own galaxy. In that instant, the known universe expanded from 100,000 light-years across to millions of light-years. Andromeda wasn't a cloud of gas in our galactic neighborhood. It was an entire galaxy in its own right, containing billions of stars. But Hubble's discoveries were just beginning. As he studied more and more distant galaxies, he noticed something extraordinary. The light from these galaxies was shifted toward the red end of the spectrum, and the more distant the galaxy, the greater the redshift. This could only mean one thing: the galaxies were racing away from us, and the farther away they were, the faster they were receding. This observation led to what we now call Hubble's law. The recession velocity of a galaxy is proportional to its distance. A galaxy twice as far away is moving away twice as fast. This pattern could only be explained by one remarkable conclusion: the universe itself is expanding. Space itself is stretching, carrying the galaxies along with it, like raisins in rising bread dough. This discovery revolutionized our understanding of cosmic history. If the universe is expanding now, it must have been smaller in the past. Wind the clock back far enough, and everything we can see must have been compressed into an infinitesimally small point. A moment of creation that we now call the Big Bang, which occurred 13.8 billion years ago. The story of how we mapped our galaxy is itself a tale of human ingenuity spanning centuries. Galileo was the first to turn a telescope skyward in 1609, resolving what appeared to be the Milky Band of the Milky Way into countless individual stars. But he had no idea of the true structure he was observing. It was William Herschel who first attempted to map our galactic home systematically. In 1785, he began the ambitious project of counting stars in different directions across the sky, trying to determine the shape and extent of what he called the sidereal system. His method was simple but brilliant. He assumed that regions with more stars were closer to the center of the system, while regions with fewer stars were toward the edge. But Herschel's map had the sun at the center of the galaxy, which seemed suspicious. It wasn't until 1918 that Harlow Shapley solved this puzzle. Shapley studied globular clusters. those ancient spherical cities of stars that orbit in the galactic halo. By measuring distances to these clusters using Cepheid variables, he discovered that they were arranged in a sphere around a point that was nowhere near the Sun. This point, Shapley realized, had to be the true center of the galaxy. The Sun wasn't at the galactic center at all. It was positioned off to one side, in what we now know are the galactic suburbs. Our perspective from within the disk had fooled earlier astronomers into thinking we were at the center of things. Today, we have tools that would seem magical to those early galaxy mappers. The European Space Agency's Gaia mission, launched in 2013, is creating the most precise three-dimensional map of our galaxy ever attempted. Gaia measures the precise positions and motions of over 1.7 billion stars, tracking their movements with such accuracy that it can detect stellar motions equivalent to watching a quarter on the Moon from Earth. These modern observations reveal details that earlier generations could never have imagined. We can now trace the intricate structure of the spiral arms, map the distribution of dark matter, and even detect the gravitational waves from colliding black holes that ripple across the galaxy. The Milky Way, we've learned, has an estimated age of between 13 and 13.8 billion years, almost as old as the universe itself. Our galaxy formed relatively early in cosmic history, condensing from primordial gas clouds just a few 100 million years after the Big Bang. And now we know we're not alone in the cosmic neighborhood. Our closest galactic neighbor, Andromeda, stretches approximately 137,000 light-years across and contains roughly 1 trillion stars, significantly more than our own Milky Way's estimated 400 billion stars. The distance between our two galaxies is about 2.5 million light-years, roughly 25 times the diameter of the Milky Way itself, a truly intergalactic separation. Andromeda's central black hole is a monster compared to our own Sagittarius A star. With a mass 25 times greater than our galactic center's black hole, it represents one of the most massive objects we know of in our local cosmic neighborhood. And this massive galaxy is heading straight toward us. Andromeda approaches the Milky Way at approximately 300,000 miles per hour. This might sound alarming, but at cosmic scales, this collision is scheduled for the distant future, approximately 4 billion years from now. When that collision occurs, it will be one of the most spectacular events imaginable, though any hypothetical observers would need to be patient, as the merger will unfold over hundreds of millions of years. Remarkably, when these two galaxies collide, individual stars will rarely actually crash into each other. The spaces between stars are so vast that most will simply pass by each other like ships in a cosmic night. Instead, the gravitational interaction will scramble stellar orbits, flinging some stars into intergalactic space, while others spiral toward the combined galactic center. The result will be a giant elliptical galaxy that astronomers have already nicknamed Milkomeda or Lactomeda. Both Andromeda and the Milky Way are the dominant members of what we call the local group, a gravitationally bound collection of galaxies that represents our immediate cosmic neighborhood. This local group spans approximately 10 million light-years from end to end and contains over 50 known galaxies, though most are small dwarf galaxies that orbit around the two larger spirals. But here's what's truly mind-bending. This local group, vast as it seems, is merely our immediate cosmic neighborhood, an infinitesimal fraction of the true scale of the universe. To understand just how small our local group actually is, let me introduce you to some of the true giants of the cosmos. Far beyond our galactic neighborhood lies a galaxy called IC 1101, a cosmic monster that stretches approximately 3.7 million light-years across its diameter. To put this in perspective, IC 1101 is about 60 times larger than our entire Milky Way. If the Milky Way were the size of a dinner plate, IC 1101 would be an entire city. This galactic behemoth contains an estimated 100 trillion stars, roughly 500 times more stars than our home galaxy. Think about that for a moment. 500 Milky Ways, with all their billions of stars, all their potential worlds, all their possible civilizations, compressed into a single galactic structure. The scale becomes almost impossible to comprehend using familiar references. If IC 1101 somehow replaced our Milky Way, it would completely engulf the Andromeda galaxy at its distance of 2.5 million light-years away. Andromeda, which we think of as a separate galaxy racing toward us across intergalactic space, would actually be located well within the boundaries of this cosmic giant. The collision we're expecting in 4 billion years would never happen. Andromeda would simply be another region within the same galactic structure. But even IC 1101 is dwarfed by truly extreme galactic structures. The galaxy Alcyonius stretches an almost incomprehensible 10.1 million light-years from end to end. This cosmic colossus is about 4 times larger than IC 1101 and roughly 163 times bigger than our Milky Way. If you could travel at the speed of light, it would take you over 10 million years just to cross from one side of Alcyonius to the other. Then there's Hercules A, an elliptical galaxy with an estimated diameter of about 900,000 light-years. While smaller than the previous giants, Hercules A demonstrates the incredible power that can lurk at galactic centers. This galaxy shoots jets of superheated material across more than 600,000 light-years of space. Streams of energy so powerful they dwarf anything we see in our own galactic neighborhood. These radio jets reveal the awesome power of supermassive black holes. The central black hole in Hercules A accelerates matter to nearly the speed of light and launches it in narrow beams that maintain their coherence across distances larger than our entire local group. These cosmic blowtorches demonstrate energies that make our sun look like a flickering candle. One of the most puzzling giants is the galaxy designated a 2261 BCG, which spans about 600,000 light-years across and contains more than 10 trillion stars. What makes this galaxy particularly mysterious is that astronomers cannot find the supermassive black hole that should exist at its center. Every galaxy this massive should have a central black hole containing millions or billions of solar masses. Yet a 2261 BCG appears to lack one entirely. This challenges our fundamental understanding of how galaxies form and evolve. These galactic giants didn't start out so massive. They grew through a process that astronomers sometimes describe as cosmic cannibalism. Like cosmic snowballs rolling through space, large galaxies gradually absorb smaller neighbors over billions of years. IC 1101, for instance, likely formed through the merger of dozens of smaller galaxies, each perhaps the size of our Milky Way or Andromeda. Every time two galaxies collide and merge, the result is larger and more massive than either predecessor. This process continues today throughout the universe. The Tadpole Galaxy shows us what happens when galactic encounters go wrong. This spiral galaxy has been stretched into an elongated shape with a tail of stars extending for hundreds of thousands of light-years. A smaller galaxy passed too close, and gravitational forces pulled streams of stars away from the main galactic body, creating a cosmic tail that will eventually disperse into intergalactic space. When you consider the galactic hierarchy, our Milky Way occupies an interesting position. It's definitely among the larger galaxies in the universe. Most galaxies are actually much smaller dwarf systems containing only millions or billions of stars rather than hundreds of billions. but compared to the true cosmic giants, our galaxy remains firmly in the middle tier. We're large enough to be respectable, but nowhere near the scale of the supermassive ellipticals that dominate galaxy clusters. And that brings us to an even grander scale of cosmic organization. Most galaxies don't exist in isolation. They gather together in groups and clusters, bound by their mutual gravitational attraction. Small groups, like our local group, typically contain around 50 galaxies. But the universe also hosts much larger structures, galaxy clusters that contain thousands of individual galaxies, all orbiting around their common center of mass. The Virgo cluster, our nearest large galactic neighborhood, lies about 54 million light-years away and contains more than 1,300 individual galaxies. This cluster stretches approximately 15 million light-years across, larger than our entire local group. At this scale, individual galaxies become mere points of light in a vast gravitational web. Even giants like our Milky Way and Andromeda would appear as tiny specks within the Virgo cluster's enormous volume. The Coma cluster, located about 300 million light-years away, contains over 1,000 galaxies bound together in a region roughly 20 million light-years across. From this distance, our local group would be completely invisible, too small and too faint to detect even with our most powerful telescopes. But galaxy clusters don't exist in isolation either. They connect to each other through filaments, vast bridges of dark matter and galaxies that span hundreds of millions of light years. These galactic filaments form what cosmologists call the cosmic web, a vast network that permeates the entire observable universe. Between the filaments stretch cosmic voids, regions containing few or no galaxies, vast bubbles of near emptiness that can span hundreds of millions of light years. The largest structures in this cosmic web are called superclusters, collections of galaxy clusters that can contain thousands of galaxies spread across volumes hundreds of millions of light years in extent. Our local group, along with the Virgo cluster and many others, belongs to a supercluster that astronomers have named Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans approximately 500 million light-years and contains more than 100,000 galaxies. To help you visualize this scale, if the Milky Way were a single house, Laniakea would be an entire continent filled with interconnected cities and towns. This vast structure connects the Virgo cluster with the Centaurus cluster, the Great Attractor, and the Norma cluster in a gravitational network of almost unimaginable proportions. At the heart of Laniakea lies something mysterious called the Great Attractor, a region of unusually high gravitational density that influences the motion of galaxies across hundreds of millions of light years. Tens of thousands of galaxies flow toward this region like cosmic rivers converging toward the sea. Our own Milky Way is part of this flow, racing through space at about 370 miles per second in the direction of the Great Attractor. The Great Attractor itself is hidden behind the dust and gas of our own galactic disk, making it difficult to observe directly. But its gravitational influence is unmistakable. It's as if there's a massive concentration of matter pulling on everything in our cosmic neighborhood, warping the flow of galaxies across a significant fraction of the observable universe. This mysterious region represents one of the largest gravitational influences in our local cosmic environment, yet we still don't fully understand what it is or how it formed. What's remarkable about structures like Laniakea is that they represent some of the largest coherent organizations of matter in the universe. At scales much larger than superclusters, the expansion of space itself begins to dominate over gravitational attraction. Laniakea is near the upper limit of what gravity can hold together against the relentless stretching of cosmic expansion. Supercluster structures typically extend across more than 300 million light-years, and the difference in scale between a galaxy group and a supercluster is like comparing a neighborhood to an entire continent. These vast assemblages of galaxies reveal the universe's tendency toward hierarchy. Small structures combine to form larger ones, which in turn combine to form even larger ones, in a cosmic progression that continues until the expansion of space itself finally wins the battle against gravity. Between these superclusters stretch the cosmic highways, galactic filaments that connect these massive structures across billions of light-years of space. Along these filaments, galaxies align themselves like beads on a cosmic necklace, following the invisible threads of dark matter that guide their formation and evolution. The filaments themselves form a three-dimensional web that spans the entire observable universe, creating the largest scale structure we know. Separating these filaments are cosmic voids, vast bubbles of near emptiness that can span hundreds of millions of light-years across. These voids contain very few galaxies, creating regions of space that are almost perfectly dark and empty. The overall distribution resembles three-dimensional soap foam, with matter concentrated along the edges of the bubbles, while the interiors remain largely vacant. But here's something that might surprise you. Even these magnificent structures like Laniakea are temporary. Dark energy, that mysterious force causing the universe's expansion to accelerate, is gradually pulling apart the gravitational bonds that hold superclusters together. Laniakea is not a permanently bound structure, but rather a temporary association of galaxy clusters that will slowly dissolve as cosmic expansion continues to accelerate. Like a cosmic sandcastle being gradually eroded by the tide of space-time itself, Laniakea is slowly coming apart under the influence of accelerating universal expansion. In the far future, only gravitationally bound systems like our local group will remain intact, while the larger structures will stretch and fade until they're no longer recognizable. This means that future civilizations will inhabit a much lonelier universe. Billions of years from now, astronomers in distant galaxies will see fewer and fewer neighbors, as cosmic expansion carries the more distant structures beyond the observable horizon. What we can see today represents a golden age of cosmic architecture, when the largest structures are still visible and still connected. Beyond Laniakea, the cosmic web continues with even more impressive supercluster structures. The Shapley supercluster, located about 400 million light-years away, contains more than 8,000 galaxies spread across a volume that dwarfs our local cosmic neighborhood. The Perseus-Pisces supercluster stretches for more than 186 million light-years, creating chains of galaxy clusters that extend across vast regions of space. Before the 1980s, astronomers had no idea that such colossal structures existed. The technology simply didn't exist to map the three-dimensional distribution of galaxies across such enormous volumes of space. The discovery of superclusters revealed that galaxies are not randomly scattered throughout the universe, as earlier astronomers had assumed. Instead, the cosmos exhibits highly organized, hierarchical patterns that extend across the largest scales we can observe. Superclusters represent some of the largest structures in the universe that are still influenced by gravitational forces. Above this scale, only the expansion of space dominates over local gravitational attraction. These structures mark a boundary between the realm where gravity can still organize matter and the realm where cosmic expansion reigns supreme. But even superclusters are dwarfed by the galactic filaments, the largest known structures in the observable universe. These filaments consist of walls of gravitationally connected superclusters that form cosmic chains extending across hundreds of millions of light years. The filaments create a vast network of galactic highways that connect the largest concentrations of matter across cosmic distances. The first of these massive structures to be discovered was the CFA2 Great Wall, identified in 1989. This cosmic structure measures hundreds of millions of light years across, creating a wall of galaxies that extends far beyond anything astronomers had previously imagined. But the CFA2 Great Wall was just the beginning. In 2003, astronomers discovered an even larger structure, the Sloan Great Wall. This cosmic wall extends approximately 850 million light-years across, traversing enormous volumes of space and containing countless galaxies arranged in a vast sheet-like structure. The Sloan Great Wall demonstrated that the universe could organize matter on scales far larger than anyone had predicted. But these discoveries pale in comparison to what was found next. The Hercules Corona Borealis Great Wall stretches an almost incomprehensible 6.2 billion light-years from end to end. To put this in perspective, if the distance between Earth and Andromeda were 1 unit, the Hercules Great Wall would span 4,000 units. This structure is so vast that light takes over 6 billion years to travel from one end to the other. The Hercules Great Wall was discovered through an unexpected method, by mapping gamma-ray bursts, the most energetic explosions known in the universe. These gamma-ray bursts, which occur when massive stars collapse or when neutron stars collide, can be seen across billions of light-years of space. By plotting the positions of these distant explosions, astronomers discovered that they weren't randomly distributed. Instead, they clustered along this enormous cosmic wall. Gamma rays represent the most energetic form of electromagnetic radiation, and they can travel across billions of light years, essentially unchanged. This makes them perfect tracers for revealing the largest structures in the universe, structures so distant and so vast that conventional galaxy surveys cannot detect them. The existence of the Hercules Great Wall challenges one of the fundamental assumptions of modern cosmology, the cosmological principle, which states that the universe should appear homogeneous when viewed on sufficiently large scales. According to standard models, structures shouldn't exceed about 743 million light-years in extent. The Hercules Great Wall exceeds this limit by nearly 10 times, forcing astronomers to question some of their most basic theoretical assumptions. More recent discoveries have revealed even more puzzling structures. Scientists have identified a structure called ʻOumuamua, which extends approximately 6.2 billion light-years across space. ʻOumuamua is roughly 13,000 times longer than the diameter of our Milky Way galaxy, creating a cosmic structure so vast that it influences the motion of our local group through space. The gravitational pull of this distant wall of galaxies contributes to our cosmic motion, drawing us along through space as part of the overall flow of matter in the universe. In February of 2016, astronomers announced the discovery of what might be the largest structure yet found, the Boötes Great Wall, detected through the Baryon Oscillation Spectroscopic Survey. This structure appears to extend across even greater distances than previously known walls, though its exact size and properties are still being studied. These massive galactic filaments result from the gravitational influence that has been shaping the distribution of matter since shortly after the Big Bang. Small fluctuations in the density of matter in the early universe were amplified by gravity over billions of years of cosmic evolution, Like ripples in a cosmic pond, these initial perturbations grew and evolved, eventually forming the gigantic patterns we observe today. This cosmic web defines the fundamental architecture of the observable universe. Within this vast network, galaxies are merely luminous points connected by invisible threads of dark matter. The web extends as far as we can see, suggesting that the patterns we observe locally continue throughout the cosmos. Data from gamma-ray bursts and other distant phenomena suggest that these structures may be even larger than we currently detect. Our ability to map the cosmic web is limited by the brightness and distance of the objects we can observe, so there may be structures out there that are simply too faint or too far away for our current technology to reveal. The observable universe itself has a diameter of approximately 58 billion light-years. This diameter corresponds to about 17.7 billion parsecs, representing the maximum distance from which light could have reached us since the Big Bang occurred 13.8 billion years ago. The apparent inconsistency between the universe's age of 13.8 billion years and its diameter of 58 billion light-years reveals one of the most mind-bending aspects of cosmic reality. During the universe's earliest moments, space itself expanded faster than the speed of light in a process called cosmic inflation. This doesn't violate Einstein's speed limit because nothing was actually moving through space faster than light. Instead, space itself was stretching at an incredible rate. When we observe a galaxy that emitted its light 13 billion years ago, that galaxy is now actually located about 28.5 billion light-years away from us. This co-moving distance accounts for all the spatial expansion that has occurred during the light's journey to reach us. The galaxy has been carried away by the expansion of space itself, while its ancient light traveled across the cosmos to arrive at our telescopes. To help you visualize the scale we're talking about, if the Milky Way were the size of a dime, the observable universe would be roughly the size of the continental United States. That's the difference in scale between our cosmic home and the limits of everything we can possibly see. Our entire galaxy, with its 400 billion stars and all the planets that might orbit them, becomes essentially invisible when placed against the backdrop of cosmic immensity. Within this vast, observable sphere, current estimates suggest there are approximately 2 trillion galaxies. 2 trillion separate island universes, each containing billions or hundreds of billions of stars. These galaxies organize themselves into more than 80 billion groups and clusters, creating a hierarchy of structures that extends across the entire visible cosmos. The total number of stars in the observable universe reaches somewhere between 30 billion trillion and 70 billion trillion. If you started counting these stars right now, 1 star per second without stopping, you would need more time than the universe has existed just to count them all. The number is so large that it transcends any meaningful comparison to human experience. The observable universe contains approximately 10 to the 80th power atoms. This number is so vast that it exceeds the number of grains of sand on all the beaches of Earth by a factor of trillions. Every grain of sand on every beach, multiplied by trillions more, still wouldn't approach the number of atoms in the space we can observe. But here's what's truly humbling about our cosmic situation. The observable universe represents only what we can see, not necessarily all that exists. There's a boundary called the particle horizon that marks the limit, beyond which light has never had enough time to reach us. Objects beyond this horizon might exist, but they remain eternally invisible to us, hidden beyond the edge of what we can ever hope to observe. Our future limit of visibility will eventually reach about 38 billion light-years as the universe continues to age and expand. But there are an estimated 2.7 trillion additional galaxies whose light may never reach us, no matter how long we wait. These galaxies exist in regions of space that are receding from us faster than their light can approach, carried away by the relentless expansion of space itself. Current theories suggest the total universe may be infinite, or at the very least, vastly larger than the observable portion. Conservative estimates indicate the entire universe is at least 250 times larger than what we can observe. If true, this would imply a minimum diameter of about 4.3 trillion light-years for the complete cosmos. The unobservable region would be roughly 15.6 million times larger in volume than everything we can see. From this perspective, our observable universe becomes an infinitesimal bubble in a cosmic ocean of unimaginable proportions. Computer simulations of cosmic structure reveal patterns resembling three-dimensional foam, with galactic filaments forming the walls of gigantic cosmic bubbles. The structures we've discovered may represent just the tiny, visible portion of an architectural framework that extends far beyond our observational horizon. Theoretical speculation suggests that regions beyond the observable universe might contain entirely different configurations of matter and energy. Some cosmologists hypothesize that distant regions could even exhibit variations in the fundamental physical laws themselves, though this remains purely speculative. Different cosmic domains might have different values for fundamental constants, different particle physics, or even different spatial dimensions. Paradoxically, we can never transcend the barrier of the observable universe. This limitation represents both a mirror of infinite curiosity and a natural boundary to knowledge. No matter how advanced our technology becomes, no matter how long our civilization endures, there will always remain vast regions of reality that lie forever beyond our reach. The James Webb Space Telescope, our most advanced cosmic observatory, can detect galaxies located approximately 13.5 billion light-years away. This brings us tantalizingly close to observational limits, allowing us to see these distant galaxies as they appeared just 300 million years after the Big Bang, when the universe was still in its cosmic infancy. When we observe these ancient galaxies, we're essentially looking back through time itself. The light reaching us today began its journey when the universe was less than 3% of its current age. These galaxies represent some of the first large-scale structures to form after the cosmic dark ages ended and the first stars began to shine. At a scale where the observable universe equals the size of planet Earth, our Milky Way galaxy would shrink below the size of subatomic particles. In this comparison, our galaxy becomes completely invisible, smaller than the wavelength of visible light. If each observable galaxy were a grain of sand, we would have beaches covering multiple continents, and the Milky Way would represent just one imperceptible grain in that vast cosmic shore. Edwin Hubble's discovery that the universe had become much larger than previously imagined was just the beginning of our cosmic awakening. The revelation that Andromeda was a separate galaxy expanded the known cosmos from thousands to millions of light-years. Each subsequent astronomical discovery has continued to expand our perspective on universal scale, transforming our galaxy from the entirety of existence into a mere point in an unimaginable immensity. Like fireworks inaugurating the dawn of time, the Big Bang created all known reality in an instant of creation that defies human comprehension. The accelerating expansion of the universe reveals dark energy as a mysterious force dominating cosmic dynamics. Dark energy represents about 68% of the universe, dark matter 27%, with ordinary matter, the stuff of stars and planets and people, comprising only 5% of cosmic reality. Our galaxy is composed predominantly of invisible substances that we don't fully understand. Even massive structures like Laniakea are temporary on cosmic timescales. The universe continues expanding and accelerating, creating ever-increasing distances between galactic structures until our Milky Way will eventually be isolated in a progressively emptier and darker cosmos. To truly visualize cosmic scale, imagine our Milky Way reduced to the size of a common coin. At this scale, the galaxy IC 1101 would occupy the area of an entire football field. The supercluster Laniakea would cover territory equivalent to the entire continent of South America. The Sloan Great Wall would extend like a mountain range, crossing the complete Asian landmass. If each atom in the human body represented a star, we still wouldn't approach galactic scale. Multiplying the world's population by 1 trillion would approximate the number of stars in a typical galaxy. If we walked one step for every 1,000 years of human history, we would need eternity just to cross our galaxy. Traveling at the maximum possible speed, the speed of light itself, we would still need 100,000 years just to cross from one edge of our galaxy to the other. Think about that for a moment. Even moving at the ultimate speed limit of the universe, faster than anything with mass can possibly travel, our galactic home remains so vast that it would take 100 millennia to traverse. The number of observable galaxies in the universe exceeds the total number of ants that have ever lived on Earth. Each galaxy contains more stars than the total number of words spoken by all of humanity throughout our entire history. If the observable universe were an ocean, our Milky Way would be a single molecule of water floating invisibly in that cosmic sea. The time required for light to cross the observable universe exceeds the lifespan of any known star, and the distance to our observational limit surpasses any journey conceivable by human civilization. These cosmic scales completely transcend our capacity for visualization or intuitive understanding. Mathematics becomes the only tool available for navigating these unimaginable dimensions. Numbers cease to have practical meaning and transform into pure abstractions that our minds can manipulate but never truly comprehend. When we observe galaxies at 13.5 billion light-years away, we see them as they existed just 300 million years after the Big Bang. We're looking at cosmic childhood, when the first large structures were just beginning to form in a universe that was still hot and dense and very different from the cosmos we inhabit today. On a scale where the observable universe equals the entire Earth, our Milky Way would shrink below the size of subatomic particles. Our galaxy would become smaller than a proton, completely invisible even under the most powerful microscopes. If each observable galaxy were a grain of sand, we would have beaches covering multiple continents. The Milky Way would represent just one imperceptible grain in that vast cosmic shore, lost among trillions of others. Edwin Hubble's discovery fundamentally changed how humans understood their cosmic situation. The revelation that Andromeda was a separate galaxy expanded our known cosmos from thousands of light-years to millions of light-years in a single observation. Each subsequent astronomical discovery has continued to amplify our perspective on universal scale, progressively transforming our galaxy from the entirety of existence into a mere point in an unimaginable immensity. The Milky Way has undergone a complete transformation in human consciousness. Once thought to be the universe itself, our galaxy is now understood as just one small component in a cosmic architecture so vast it defies description. Like fireworks inaugurating the dawn of time, the Big Bang created all known reality in an explosive moment that gave birth to space, time, matter, and energy all at once. The accelerating expansion of the universe reveals dark energy as a mysterious force that dominates cosmic dynamics. This strange energy represents approximately 68% of everything that exists, while dark matter accounts for 27%. Ordinary matter, the atoms that form stars and planets and people, comprises only 5% of cosmic reality. Our galaxy is composed predominantly of invisible substances that we don't fully understand. Even massive structures like Laniakea are temporary when viewed on cosmic timescales. The universe continues expanding and accelerating, creating ever-increasing distances between galactic structures. Eventually, our Milky Way will be isolated in a progressively emptier and darker cosmos, with neighboring galaxies carried so far away by cosmic expansion that they disappear beyond our observational horizon. To help you visualize true cosmic scale, imagine our Milky Way reduced to the size of a common coin lying on a table. On this scale, the galaxy IC 1101 would cover an entire football field with proportional depth. The galaxy Alcyonius would stretch like a highway for 100 miles across the cosmic landscape. The supercluster Laniakea would occupy territory equivalent to the entire continent of South America in this reduced perspective. The Sloan Great Wall would extend like a mountain range, stretching across the complete Asian continent. The Hercules Corona Borealis Great Wall would circle planet Earth multiple times in this miniaturized perspective. The entire observable universe would represent the Earth's surface expanded to the size of our solar system. In this extreme analogy, our Milky Way remains just a lost coin in a continental field. If each atom in your body represented a single star, you still wouldn't approach galactic scale. Multiplying the world's entire population by 1 trillion would approximate the number of stars in a typical galaxy. The mathematical relationships become so extreme that familiar concepts lose all meaning. Consider this progression of scale. If you counted 1 star per second without stopping, you would need more than the entire age of the universe just to enumerate the stars in our galaxy alone. If you could somehow count all the atoms in the observable universe at the rate of 1 per second, you would need vastly longer than the universe has existed just to complete this impossible task. The distance scales involved surpass human comprehension. If you could build a highway from Earth to the nearest star, Proxima Centauri, and drive at interstate speeds without stopping, the journey would take you 5 million years. If you attempted to drive to the center of our galaxy at the same speed, you would need to maintain that pace for 160 million years. And to reach the nearest large galaxy cluster, the Virgo cluster, would require a journey lasting 3.5 billion years. These numbers reveal the fundamental isolation of our cosmic situation. Even traveling at the speed of light, the ultimate speed limit of physics, distances between galaxies remain so vast that intergalactic travel becomes essentially impossible. The spaces between structures grow ever larger as cosmic expansion continues, making the universe an increasingly lonely place. Yet paradoxically, this cosmic perspective doesn't diminish our significance, it redefines it completely. We are not the geographical center of the cosmos, but we may represent something far more important, conscious observers capable of contemplating the infinite. Our capacity to understand these scales transcends any physical limitation imposed by our size. Through our mathematics, the universe calculates its own properties and behavior. Through our science, 13.8 billion years of cosmic evolution comes to know itself. Through our art and culture, we express cosmic beauty in ways that inanimate matter never could. Through our emotions, we transform physical events into subjectively meaningful experiences. Our existence proves that extraordinary complexity can emerge from cosmic simplicity. We represent improbable concentrations of organization in an immensity that remains mostly empty space. The Milky Way simultaneously ranks as one of the larger galaxies in existence and as a negligible cosmic particle when viewed from universal perspectives. This duality defines our condition perfectly. We are local giants and universal atoms, creatures whose physical size renders them invisible on cosmic scales, but whose consciousness embraces the entirety of observable reality. Knowledge represents a victory of mind over the limitations of physical scale. In a cosmos spanning 58 billion light-years, we create meaning through connection and understanding. Our responsibility becomes preserving and expanding this rare manifestation of cosmic consciousness. Future generations will inherit an even broader perspective on universal structure as our technology advances and our understanding deepens. The Milky Way will remain our cosmic home even as we discover increasingly larger structures. Our journey of scientific discovery has barely begun on this universal scale. Each new revelation about the cosmos amplifies our sense of wonder while teaching us profound humility about our place in the grand scheme of existence. We represent the universe contemplating its own magnificence through human consciousness. Cosmic scale teaches us both deep humility and extraordinary pride. In the end, we understand that while our Milky Way may be erased by universal scale, our capacity to recognize this fact makes our galaxy eternally significant. The cosmic immensity is not a threat to our importance, but an invitation to contemplation and wonder that will continue as long as conscious beings exist to perceive the infinite beauty surrounding us. Astronomical numbers lose all practical meaning and transform into pure abstractions that exist only in the realm of mathematics. The Hercules Corona Borealis Great Wall currently represents the champion of known cosmic structures, but recent data suggests this structure may be even larger than previous estimates indicated. Future telescopes like Theseus will revolutionize our studies of these extreme galactic structures, potentially revealing cosmic architecture that dwarfs even our current record holders. The limited number of gamma-ray bursts available for mapping prevents us from creating complete pictures of these superstructures. It's like trying to chart an entire ocean using only a few dozen randomly scattered buoys. We have detected perhaps a few hundred gamma-ray bursts across the entire observable universe, yet we need thousands or even millions to properly map the largest cosmic structures. Each burst represents a cosmic lighthouse, briefly illuminating structures that would otherwise remain invisible across billions of light years. Future space missions will provide the data necessary for complete understanding. But until then, we can only glimpse fragments of structures that may extend across truly incomprehensible distances. The upcoming Theseus mission will detect gamma-ray bursts with unprecedented sensitivity, potentially revealing cosmic walls and filaments that make our current discoveries look modest by comparison. Structures of this magnitude challenge the fundamental cosmological models that describe universal homogeneity. The cosmological principle assumes that the universe appears homogeneous when viewed on sufficiently large scales, but structures exceeding 743 million light-years in extent are viewed with considerable caution by theoretical cosmologists. The Hercules Great Wall sits at the very limit of what current models can accommodate without requiring significant adjustments to our understanding of cosmic evolution. According to our best theories, matter should smooth out into uniform distribution at scales larger than about 700 million light-years. Yet here, we have structures that are nearly 10 times larger than this theoretical limit. It's as if we discovered mountains on a planet where our theories predicted the surface should be perfectly flat. These observations force cosmologists to reconsider some of their most fundamental assumptions about how the universe evolved. Future discoveries may reveal structures even larger than those we currently know, potentially revolutionizing modern cosmology in ways we cannot yet anticipate. Large groups of quasars may represent the precursors of galactic filaments, theoretical proto-hypercluster formations that are actively developing across cosmic time. These quasar groups span billions of light years and may be the seeds from which even larger structures will grow over cosmic ages. We observe the universe at one specific epoch in cosmic evolution, which means we lose the temporal perspective needed to understand how these structures form and change. The structures we see today represent merely a snapshot of an evolutionary process that spans billions of future years. We're witnessing cosmic architecture in the middle of its development, like archaeologists examining a single frame from a movie that has been playing for 13.8 billion years and will continue for trillions more. Computer simulations suggest that these massive structures are still growing, still evolving, still connecting across ever larger scales. What we see as distinct walls and filaments today may eventually merge into even more colossal structures that we cannot yet imagine. The universe is still young, still organizing itself into patterns that will dwarf anything we currently observe. In the face of this cosmic immensity, human existence acquires a paradoxical and profound significance. We are direct products of cosmic evolution, elements literally forged in the interior of ancient stars that lived and died billions of years before our sun was born. The carbon atoms in our DNA formed through nuclear fusion in massive stellar cores that burned for millions of years before exploding as supernovas. The oxygen we breathe was created during supernova explosions that occurred billions of years ago. These stellar detonations scattered enriched material across thousands of light years, seeding space with the heavy elements necessary for planet formation and life. The calcium in your bones formed in stellar cores, where temperatures reached hundreds of millions of degrees Fahrenheit. The iron in your blood was forged under pressures that would crush any earthly material. Every atom in your body has traveled through intergalactic space during cosmic eons. Before becoming part of you, these atoms drifted through the cosmic void for billions of years, carried by stellar winds, scattered by supernova explosions, gradually incorporated into new generations of stars and planetary systems. You are assembled from cosmic debris that has witnessed the formation of galaxies, the birth and death of countless stars, the collision of galactic clusters. The phosphorus enabling your thoughts to occur was created in the final moments of a massive star's life. The sulfur in your proteins formed during explosive nucleosynthesis when ancient stars died. Even the trace elements in your body, the zinc, the copper, the selenium, each has its own stellar origin story spanning billions of years of cosmic history. Our consciousness represents the universe becoming self-aware of its own existence. Through our perception, the cosmos contemplates its own immensity and structural complexity. When you look up at the night sky and feel wonder at the stars, you're experiencing the universe marveling at itself. When you study astronomy or cosmology, you are participating in the cosmos's attempt to understand its own nature. Humanity constitutes the universe's attempt to understand its own origins and ultimate destiny. Our scientific capacity enables the cosmos to map its own large-scale architecture through the instruments and theories we create. Every telescope we build extends the universe's ability to observe itself. Every equation we solve reveals another aspect of cosmic self-knowledge. Our telescopes function as the universe's eyes, observing its own historical evolution. When we point the James Webb Space Telescope toward distant galaxies, we enable the cosmos to examine its own childhood, to witness its own formation and development across cosmic time. The light captured by our instruments carries information about cosmic conditions that existed billions of years ago, allowing the universe to literally see its own past. Human mathematics decodes the fundamental language in which cosmic reality is written. The equations we derive describe the behavior of matter and energy across scales from subatomic particles to galactic clusters. When Einstein formulated general relativity, he was discovering the mathematical grammar that governs space and time themselves. When Hubble measured galactic redshifts, he was reading the cosmic story written in the language of expanding space. Our scientific curiosity echoes a cosmic need for self-knowledge and understanding. The drive to explore, to question, to seek truth may represent the universe's own impulse toward greater awareness. Human civilization represents a local flowering of universal complexity, a concentration of organization and information processing that emerges from the cosmos itself. Culture, art, and knowledge are expressions of cosmic creativity manifesting itself locally through conscious beings. When Mozart composed a symphony, he was channeling the same creative impulse that shapes galaxies and builds complex structures from simple elements. When Shakespeare wrote poetry, he was giving voice to the universe's capacity for beauty and meaning. When we create art or music or literature, we are the cosmos expressing its own aesthetic sense. Our search for meaning may reflect a cosmic tendency toward greater complexity and organization. From the simple hydrogen and helium of the early universe, cosmic evolution has produced galaxies, stars, planets, and ultimately conscious beings capable of contemplating existence itself. We represent the current pinnacle of this complexity gradient, the most organized and information-rich structures known in the cosmos. We are the universe experiencing its own existence subjectively, transforming objective physical reality into conscious, felt experience. Without consciousness, the universe would consist merely of particles following physical laws, lacking any inner dimension or subjective appreciation of its own magnificent architecture. Through us, the cosmos gains an interior life, a capacity for wonder and meaning that transcends mere physical existence. Paradoxically, our physical insignificance may actually amplify our importance as cosmic observers. If the Milky Way represents a negligible point in cosmic immensity, what significance can human events possibly possess? Wars, discoveries, and entire civilizations unfold on scales that are subatomic compared to cosmic structures. Your entire life, from birth to death, represents an infinitesimal moment in cosmic time. The rise and fall of human empires occurs in cosmic microseconds. All of recorded history spans less than a single galactic rotation. The entire span of human civilization, from the first agricultural settlements to the present day, represents less than 1/100% of the time our galaxy has existed. In cosmic terms, human history is briefer than a single heartbeat. Yet this perspective doesn't diminish human significance. It transforms our understanding of what significance means. Perhaps we are not meant to be cosmically large, but rather cosmically aware. Our significance may lie not in our size, but in our capacity to perceive, understand, and appreciate the universe that created us. We are small enough to exist within cosmic structures, yet conscious enough to comprehend their full extent. Consciousness introduces concepts like beauty, truth, and meaning into physical reality. Without observers like us, the universe would consist merely of configurations of matter and energy following physical laws, lacking any subjective experience or appreciation of its own magnificent complexity. We are the universe's way of knowing itself, of transforming objective existence into subjective meaning. Through our science, 13.8 billion years of cosmic evolution comes to understand itself. Through our art, we express cosmic beauty in ways that inanimate matter could never achieve. Through our relationships and emotions, we create meaning from physical interactions, transforming the mechanical dance of atoms into love, wonder, and purpose. Through our capacity for awe, we give the universe a way to be amazed by its own grandeur. Perhaps consciousness and intelligence represent the universe's greatest achievements. In a cosmos composed mostly of empty space and dark matter, the emergence of beings capable of contemplating infinity represents an extraordinary triumph of organization over entropy, of meaning over mechanism. We are rare concentrations of awareness in an immensity that remains predominantly unconscious. We are simultaneously cosmic giants and cosmic atoms, local concentrations of complexity in an immensity that remains predominantly empty and dark. Our significance lies not in competing with cosmic scale, but in complementing it. We provide the universe with something it cannot achieve through size alone: the capacity for self-reflection and appreciation. In contemplating cosmic scale, we discover that size and significance operate on different dimensions. Physical magnitude and meaning exist in separate realms. Our cosmic journey reveals that being small in space does not mean being small in importance. In fact, our very ability to recognize our cosmic smallness may be what makes us cosmically significant. However, consciousness and subjective experience may represent fundamental aspects of reality itself. Perhaps the universe exists precisely to enable the emergence of conscious observers, a speculative but intriguing hypothesis that transforms our understanding of cosmic purpose. The anthropic principle suggests that the physical constants of our universe appear fine-tuned with extraordinary precision to permit the existence of complex life. Consider the delicate balance required for our existence. If the strong nuclear force were just 5% weaker, stars could never form because hydrogen nuclei wouldn't bind together to create helium. If it were 5% stronger, hydrogen would have been consumed so rapidly in the early universe that stars would burn out before planets could form. If the electromagnetic force was slightly different, atoms couldn't maintain their structure. If gravity were marginally stronger, the universe would have collapsed back on itself before galaxies could form. Minute alterations in any fundamental force would prevent the formation of atoms, stars, and planets. The ratio between the electron mass and proton mass, the strength of the weak nuclear force, the cosmological constant that governs universal expansion, dozens of physical parameters fall within narrow ranges that allow complexity to emerge. Change any one of these values by a small percentage, and the universe becomes sterile, incapable of producing anything more interesting than hydrogen gas. Our existence might represent a necessary condition for the universe to acquire objective meaning. Without conscious observers, the universe would consist merely of configurations of matter and energy, following physical laws without purpose, at least from a philosophical perspective. The emergence of consciousness introduces concepts like beauty, truth, and meaning into physical reality, transforming mechanical processes into something infinitely richer. Perhaps we are active participants in the continuous creation of cosmic meaning. Our microscopic scale enables a unique perspective on the totality of existence. Like cosmic microscopes, we reveal details that remain invisible at larger scales. We can perceive individual atoms, study quantum mechanics, explore molecular biology, and understand processes that operate far below the threshold of galactic or cosmic awareness. Advanced civilizations may represent the universe's method of developing intelligence. Our scientific journey operates simultaneously as external exploration and internal discovery. To understand the cosmos means understanding our own fundamental nature, since we are products of cosmic evolution. Human love might represent a poetic manifestation of the same cohesive forces that maintain cosmic organization, the tendency for complex systems to bind together and create order from chaos. Our search for truth echoes a universal need for order emerging from chaos. We are physically minuscule, yet our consciousness embraces the entirety of cosmic immensity. Our existence proves that the universe can create extraordinary complexity from fundamental simplicity. We represent a triumph of organization over entropy, of life over inert matter, of consciousness over unconscious mechanism. Our scientific journey demonstrates the cosmic capacity for self-knowledge through conscious components. We occupy a simultaneously insignificant and unique position as cosmic observers. Now we return to our initial question: how large is the universe compared to our galaxy? The Milky Way, our gigantic cosmic home, is literally erased by universal scale. Within the observable universe, our galaxy occupies a fraction smaller than a grain of sand on an entire beach. If the universe were a vast library, the Milky Way would represent a single letter lost on a single page. Paradoxically, this perspective doesn't diminish our importance, but completely redefines it. We are not the geographical center of the cosmos, but we may represent the center of meaning itself. Our capacity to contemplate infinity makes us special, regardless of our physical location. Civilizations like ours might be extraordinarily rare, even in a universe containing trillions of galaxies. Perhaps we represent a cosmic experiment in creating intelligence and self-consciousness. Our science enables 13.8 billion years of cosmic evolution to know itself. Through our mathematics, the universe calculates its own properties and behavior. Through our art, we express cosmic beauty in ways that inanimate matter could never achieve. Through our emotions, we transform physical events into subjectively meaningful experiences. Our existence demonstrates that extraordinary complexity can emerge from cosmic simplicity. We are improbable concentrations of organization in an immensity that remains predominantly empty space. The density of organized information in a human brain exceeds the information density found anywhere else in the known universe. In a cubic inch of brain tissue, there are approximately 100 billion neural connections, more connections than there are stars in our galaxy. Every thought you have, every memory you form, every moment of consciousness represents the universe achieving a level of self-organization that surpasses anything we observe in galactic clusters or cosmic filaments. Your awareness right now, as you contemplate these cosmic scales, represents the most complex known process in the observable universe. The biological complexity that enables human consciousness emerges from cosmic simplicity through billions of years of evolution. The same physical laws that govern galactic rotation also govern the folding of proteins in your cells. The same fundamental forces that hold atomic nuclei together also enable the electrochemical processes of thought and memory. You are built from the same materials as stars and planets, yet organized in ways that achieve something stars and planets cannot: subjective experience of existence. Consider the remarkable journey that led to your consciousness. Hydrogen atoms formed in the first few minutes after the Big Bang eventually became part of massive stars. These stars burned for millions of years, fusing hydrogen into heavier elements through nuclear processes that required temperatures of hundreds of millions of degrees. When these stars exploded as supernovas, they scattered enriched material across thousands of light years of space. This stellar debris gradually collected into new solar systems, where planets formed from the accumulated dust of dead stars. On at least one of these planets, complex chemistry emerged that eventually led to self-replicating molecules. Over billions of years, these molecules evolved into increasingly complex forms, eventually producing organisms capable of sensation, memory, learning, and finally, consciousness. The chain of cosmic events required for your existence spans the entire history of the universe. Every step in this process had to occur with extraordinary precision for consciousness to emerge. The universe had to expand at exactly the right rate. Stars had to form with the right masses. Planets had to form at the right distances from their stars. Chemistry had to evolve in exactly the right directions. Yet here you are, a temporary arrangement of cosmic materials that has achieved awareness of its own cosmic context. You represent approximately 7 octillion atoms organized in such a way that they can contemplate the organization of 2 trillion galaxies across 58 billion light-years of space. The information processing capacity of human consciousness may represent the universe's most sophisticated achievement. Your brain contains roughly 86 billion neurons, each connected to thousands of others, creating a network more complex than any structure we observe in the cosmic web. The thoughts occurring in your mind as you read these words involve electrochemical processes more intricate than the gravitational dynamics that govern galactic clusters. Through human consciousness, the universe achieves something that pure size cannot provide. We give the cosmos a subjective interior, a capacity for wonder and appreciation that transcends mere physical magnitude. When you feel awe at cosmic scale, you are experiencing the universe marveling at itself through your consciousness. Our scientific instruments extend our cosmic awareness far beyond biological limitations. The James Webb Space Telescope essentially functions as an extension of human vision, allowing us to see light that has traveled for over 13 billion years. Our radio telescopes detect signals from cosmic phenomena that occurred before Earth existed. Through our mathematics and observations, we map cosmic territories that our bodies could never visit. Mathematics serves as our cosmic language, enabling navigation through dimensions our intuition cannot grasp. When we calculate the mass of distant galaxies or the age of the universe, we are using abstract thinking to understand concrete reality across scales that span 40 orders of magnitude. From subatomic particles to cosmic superclusters, human mathematics provides tools for comprehending existence at every level. The equations describing quantum mechanics apply to processes inside your neurons. The same mathematical principles governing general relativity shape the space-time through which your thoughts move. Mathematics represents a bridge between the microscopic realm of consciousness and the macroscopic realm of cosmic structure. Our position as cosmic observers grants us unique privileges and responsibilities. We can appreciate beauty in ways that transcend survival needs. We can pursue truth for its own sake, rather than merely for practical advantage. We can create art, music, literature, and philosophy that express cosmic themes through human experience. Perhaps most remarkably, we can feel love and compassion for other conscious beings, creating networks of care and meaning that operate on emotional rather than purely physical levels. These emotional connections may represent the universe's capacity for self-care, expressing itself through conscious beings who can value each other's existence. The rarity of consciousness in the cosmic context makes every moment of awareness precious beyond measure. If civilizations like ours occur only rarely across cosmic scales, then every human thought and feeling represents an extraordinary cosmic achievement. Your capacity to understand these cosmic scales, to feel wonder at their magnitude, to appreciate the beauty of cosmic architecture, this makes you a precious and irreplaceable part of cosmic evolution. In the end, we discover that cosmic scale doesn't diminish human significance, but reveals its true nature. We are not important because we are large, but because we are aware. Not significant because we dominate cosmic space, but because we can contemplate cosmic space and find it beautiful. Our smallness enables rather than prevents our cosmic significance, allowing us to serve as the universe's capacity for self-reflection and appreciation. The Milky Way exists simultaneously as one of the largest galaxies in the universe and as a negligible cosmic particle. This paradoxical duality defines our fundamental condition perfectly. We are local giants and universal atoms, creatures whose physical scale renders them invisible in cosmic terms, yet whose consciousness embraces the entirety of observable reality. Cosmic scale doesn't negate human importance, but reveals its truly extraordinary nature. Our capacity to understand the cosmos transcends any physical limitation imposed by size. Scientific knowledge represents a victory of mind over the constraints of bodily scale. In a cosmos spanning 58 billion light-years, we create meaning through connection and understanding that operates entirely independently of physical magnitude. Our responsibility becomes preserving and expanding this rare manifestation of cosmic consciousness. We serve as guardians of the universe's capacity for self-awareness, carrying forward the improbable achievement of matter organizing itself into patterns capable of contemplating existence itself. Future generations will inherit an even broader perspective on universal structure as our technology advances and our understanding deepens. The Milky Way will remain our cosmic home even as we comprehend increasingly larger structures. Our journey of scientific discovery has barely begun on this universal scale. Each new revelation about the cosmos amplifies our sense of wonder while teaching us profound humility about our place in the grand architecture of existence. We represent the universe contemplating its own magnificence through human consciousness. Cosmic scale teaches us both deep humility and extraordinary pride simultaneously. We are humbled by our physical insignificance, yet proud of our cognitive achievements. In the end, we understand that while the Milky Way may be erased by universal scale, our capacity to recognize this fact makes our galaxy eternally significant. The cosmic immensity surrounding us is not a threat to our importance, but rather an invitation to contemplation that will continue as long as conscious beings exist to perceive infinite beauty. The more we learn about the universe, the more we recognize how improbable our existence actually is. We are unique witnesses to a cosmos that without us would be merely physics without narrative, mechanism without meaning. The Milky Way has harbored not only our biological evolution, but also our cultural and scientific evolution. Over the past 4.5 billion years, our galactic environment has remained stable enough to allow complex chemistry to develop on Earth, life to emerge and evolve, and eventually intelligence to arise and begin studying its cosmic context. Every telescope we construct expands our vision beyond galactic limitations. The Hubble Space Telescope revealed galaxies existing billions of light-years beyond our local cosmic neighborhood. The James Webb Space Telescope now shows us the universe as it appeared when cosmic structures were just beginning to form. Future instruments will extend our reach even further, potentially revealing cosmic architecture that dwarfs even the largest structures we currently know. Each equation we solve deciphers another secret of universal architecture. When Newton formulated his law of gravitation, he revealed the force that holds galaxies together. When Einstein developed general relativity, he exposed the geometric nature of spacetime itself. When Hubble discovered cosmic expansion, he revealed the dynamic history of the entire universe. Our mathematical tools enable us to understand cosmic processes that occur across scales from subatomic to intergalactic. The stellar density in our galaxy falls dramatically beyond a radius of about 25,000 light-years from the galactic center. In the outer regions, stars become as sparse as isolated islands in a cosmic ocean. Individual stars may be separated by dozens of light-years, creating vast regions of near emptiness, where interstellar travelers would see only the most distant pinpricks of light. But these galactic scales represent merely the first step in a cosmic ladder that extends far beyond our current comprehension. We have detected regions of intense gamma-ray emission, extending approximately 15,000 light-years above and below the galactic disk. These mysterious structures suggest extreme energetic activity in the galactic center's past, possibly related to the feeding and growth of our central supermassive black hole. These gamma-ray bubbles dwarf any earthly conception of scale. They extend farther from the galactic plane than our solar system is from the galactic center, representing structures so vast they encompass millions of solar systems within their boundaries. The energy required to create these bubbles exceeds anything we observe in our current galactic environment, suggesting that our galaxy's past was far more violent and energetic than its present relatively calm state. The discovery of these structures reminds us that even our home galaxy contains mysteries that challenge our understanding. We live within a cosmic structure that we are only beginning to comprehend fully. The Milky Way continues to surprise us with new discoveries. Streams of stars being torn from satellite galaxies, dark matter clumps passing through the galactic disk, high-velocity clouds of gas raining down from the galactic halo. Our galaxy exists in a delicate balance between opposing forces. Gravity pulls matter inward toward the galactic center, while rotation and random stellar motions prevent complete collapse. Dark matter provides the gravitational scaffolding that maintains galactic structure, yet we understand almost nothing about its true nature. Magnetic fields thread through the galactic disk, channeling the flow of charged particles and influencing star formation patterns. The interstellar medium, the thin gas and dust between the stars, plays a crucial role in galactic ecology. This material, enriched by stellar deaths and supernova explosions, provides the raw material for new generations of stars and planetary systems. Our solar system formed from such recycled material, incorporating atoms that had been processed through multiple stellar generations. Every breath you take contains oxygen atoms that were forged in stellar cores and distributed through space by supernova explosions. The calcium in your bones was created through nuclear fusion in massive stars that died billions of years ago. The iron in your blood formed during the final moments of stellar collapse, when temperatures and pressures reached extremes that no earthly laboratory can replicate. This material connection links us intimately to our galaxy's chemical evolution. We are not separate from the Milky Way, but integral parts of its ongoing development. Through biological processes, our galaxy has achieved a form of self-organization that enables conscious reflection on its own structure and history. The timescales involved in galactic evolution dwarf human comprehension. Our galaxy has completed only about 60 rotations since its formation 13 billion years ago. The spiral arms we see today are temporary features that form and dissolve over hundreds of millions of years. Stars migrate radially through the galactic disk, following complex orbital patterns influenced by spiral density waves and gravitational perturbations. Our solar system's current location in the galactic disk is temporary. Over cosmic time, we drift through different galactic environments, sometimes passing through spiral arms where star formation is active, sometimes traversing quieter regions between the arms. These changing galactic neighborhoods may have influenced Earth's climate and biological evolution in ways we are only beginning to understand. The Milky Way itself is evolving. It continues to accrete smaller satellite galaxies, gradually growing in mass and size. The ongoing merger with the Sagittarius dwarf galaxy is slowly distorting our galaxy's disk structure. In the far future, our collision with Andromeda will completely transform the galactic landscape, creating a new cosmic environment unlike anything currently existing. Yet through all these changes, the fundamental cosmic principles remain constant. Gravity continues to organize matter into increasingly complex structures. Nuclear fusion powers the stars that illuminate the cosmic darkness. The interplay between matter and energy drives the ongoing evolution of cosmic architecture. As conscious observers within this vast cosmic machinery, we occupy a unique position. We can observe galactic processes that unfold over millions of years, understand stellar life cycles that span billions of years, and contemplate cosmic evolution that extends across the entire age of the universe. Our brief individual lifespans enable us to glimpse eternal processes and find meaning in our temporary participation in cosmic development. The Milky Way has nurtured the conditions necessary for our emergence. Its chemical evolution provided the heavy elements required for rocky planets. Its relatively stable environment allowed complex chemistry to develop over geological timescales. Its position in the cosmic web placed us in a region where matter density is neither too high nor too low for the formation of long-lived stellar systems. In contemplating our galactic home, we realize that understanding cosmic scale requires both scientific knowledge and philosophical reflection. The numbers alone cannot convey the full significance of existing within such vast structures. Mathematics provides the tools for measurement, but consciousness provides the capacity for appreciation and meaning. We are the Milky Way's way of knowing itself. Through our observations and theories, our galaxy achieves self-awareness of its own structure, history, and cosmic context. This makes us integral participants in cosmic evolution rather than mere observers of processes that occur independently of our consciousness. More than half of the molecular gas in the Milky Way concentrates in clouds similar to the Orion Nebula. These regions function as stellar nurseries where new stars are continuously born from collapsing gas and dust. If you could visit the Orion Nebula, located about 1,300 light-years away, you would witness stellar birth in action. New stars emerge from dense knots of gas and dust, igniting nuclear fusion as their cores reach temperatures of 18 million degrees Fahrenheit. Our galaxy operates as a living system, recycling stellar material into new generations of stars and planets in an endless cycle of cosmic renewal. When massive stars reach the end of their lives and explode as supernovas, they scatter enriched material across thousands of light-years of space. This stellar debris gradually collects into new molecular clouds where the next generation of stars will form, incorporating the heavy elements created in their stellar predecessors. The main galactic disk possesses an average thickness of only about 621 miles, remarkably thin compared to its overall diameter. If the Milky Way were a compact disk, its thickness would represent only 1% of its total diameter. This flattened structure results from galactic rotation and the conservation of angular momentum, as matter collapsed into the disk billions of years ago. Picture our galaxy as a cosmic pizza, with most of the visible stars confined to a layer thinner than the crust. This extreme flatness developed as the early galaxy collapsed under its own gravity while spinning, much like a ball of dough flattening into a pizza when spun rapidly. The centrifugal force from rotation prevented complete gravitational collapse, creating the thin disk structure we observe today. Stars orbit the galactic center in complex trajectories, influenced by the invisible dark matter that permeates our galaxy. These stellar orbits are not simple ellipses like planetary orbits around the Sun, but rather complex rosette patterns that precess over millions of years. Our solar system bobs up and down through the galactic plane as it orbits, crossing the disk's midline every 33 million years. This invisible halo of dark matter extends far beyond the visible stars, creating a gravitational framework that holds everything together. The dark matter halo surrounding our galaxy spans approximately 600,000 light-years, 6 times larger than the visible disk. Without this invisible scaffolding, the Milky Way would disintegrate, unable to maintain gravitational coherence as it rotates. We literally live within an invisible network that we don't fully understand. The rotation curve of our galaxy reveals dark matter's presence. If only visible matter existed, stars in the outer regions should orbit much more slowly than those near the center, following Kepler's laws like planets in our solar system. Instead, stars maintain roughly constant velocities regardless of their distance from the galactic center, indicating that enormous amounts of invisible mass must exist in the galactic halo. The total mass of the Milky Way, including dark matter, reaches approximately 1.5 trillion solar masses. This staggering number means our galaxy contains enough material to create 1.5 trillion copies of our Sun. Yet remarkably, about 90% of this mass remains completely invisible, detectable only through its gravitational effects on visible matter. About 1 in every 10 stars in our galaxy are white dwarfs, dense remnants of stars similar to our Sun that have exhausted their nuclear fuel and collapsed to Earth-sized objects containing solar masses of material. These stellar corpses represent the ultimate fate awaiting the vast majority of stars in our galaxy. Few white dwarfs have been detected due to their extremely low luminosity and reduced size. They shine only from residual heat left over from their stellar deaths. A typical white dwarf contains the mass of our entire Sun, compressed into a volume roughly equal to Earth's. The matter becomes so dense that a sugar cube of white dwarf material would weigh as much as a large automobile on Earth. The surface gravity becomes hundreds of thousands of times stronger than Earth's gravity, making white dwarfs among the most extreme environments in the galaxy. These dense objects represent the future destiny of our own Sun in approximately 5 billion years. Before becoming a white dwarf, the Sun will transform into a red giant, possibly expanding to engulf Earth's orbit. During this red giant phase, our star will swell to hundreds of times its current size as it exhausts hydrogen fuel in its core and begins burning helium in concentric shells. As the Sun expands into a red giant, it will likely engulf Mercury and Venus completely. Earth's fate remains uncertain. It might be swallowed by the expanding solar atmosphere or perhaps pushed into a more distant orbit by the Sun's decreasing mass. Earth will become uninhabitable long before this occurs, with our oceans evaporating in roughly 1 billion years as the Sun gradually grows brighter during its main sequence evolution. The final stages of solar evolution will be spectacular from any surviving vantage point. The Sun will eject its outer layers in a series of thermal pulses, creating a beautiful planetary nebula, a glowing shell of ionized gas expanding into interstellar space. At the center will remain a hot white dwarf, slowly cooling over trillions of years until it becomes a cold, dark cinder. But the Milky Way will continue existing, eventually merging with Andromeda to form the future galaxy astronomers have nicknamed ʻOumuamua. This galactic collision will begin in earnest in approximately 4 billion years, unfolding over hundreds of millions of years as the two spiral galaxies approach, interact, and finally merge into a single elliptical system. This combined galaxy will dominate the local group for trillions of years to come. Other galaxies in our local group will either be absorbed into Milky or remain as satellite galaxies orbiting the merged system. The Triangulum galaxy, our local group's third largest member, will likely be incorporated during this cosmic merger. Individual stars rarely collide even during violent galactic mergers. The space between stars is so vast that they pass by each other like cosmic ghosts, their gravitational interactions reshuffling orbital patterns without direct stellar contact. However, planetary systems may be gravitationally disturbed during the merger process, with planets potentially being stripped from their parent stars or flung into altered orbits. Computer simulations of the Milky Way-Andromeda collision show a complex dance of gravitational forces. As the two galaxies approach, tidal forces will begin stretching both systems, creating vast streams of stars extending millions of light years into intergalactic space. These stellar streams will eventually fall back and be incorporated into the merged galaxy. Earth and our solar system might be ejected to the outer regions of the resulting galaxy, or perhaps hurled toward the galactic center where stellar density and energetic activity are much higher. Our final location will depend on complex gravitational interactions that are impossible to predict precisely. Regardless of our destination, the night sky viewed from Earth would be unrecognizably different from what we see today. During Andromeda's approach, that galaxy would dominate our sky, spanning dozens of degrees and appearing as a magnificent spiral structure visible to the naked eye. Even now, Andromeda appears as a faint oval patch in the constellation of the same name, but during the collision, it would fill much of the night sky with its spiral arms and central bulge clearly visible. The galactic merger would unfold over hundreds of millions of years, with hypothetical witnesses observing the sky's gradual transformation across countless generations. The process would be slow enough that individual human lifespans would detect little change, but over geological timescales, the heavens would be completely transformed. New stars would be born abundantly as gas clouds from both galaxies collide and compress. The collision of molecular clouds would trigger intense star formation, creating brilliant stellar nurseries throughout the merging system. The star formation rate would increase dramatically during the peak of the merger, as gravitational forces trigger widespread stellar birth throughout the combined galactic structure. These newly formed stars would be predominantly massive, hot and blue, living brief but brilliant lives before exploding as supernovas. The increased supernova rate would flood the galaxy with high-energy radiation and heavy elements, potentially affecting any life forms that might exist during this cosmic upheaval. Eventually, however, the available gas would be exhausted and star formation would cease. The resulting galaxy would be predominantly populated by ancient reddish stars, long-lived, low-mass stars that burn their nuclear fuel slowly and can shine for trillions of years. The vibrant blue stars that trace spiral arms would have long since died, leaving behind white dwarfs, neutron stars, and black holes. Trillions of years in the future, the universe will become a much darker and colder place. Massive stars will have all died, leaving only red dwarfs, the smallest and longest-lived stars, to shine for trillions of years. These dim red stars will be the last stellar lights in an increasingly cold and empty universe. The eventual death of the last stars will mark the end of the universe's stellar era. As red dwarfs finally exhaust their nuclear fuel, they too will become white dwarfs, and then eventually cold black dwarfs, dark, dense remnants, invisible against the cosmic background. Star formation will have ceased entirely, as all available hydrogen is either locked up in stellar remnants or dispersed too thinly to collapse under gravity. Black holes will dominate the future cosmos, slowly evaporating through Hawking radiation over unimaginably long timescales. Even the most massive black holes, containing billions of solar masses, will eventually evaporate completely. The process is incredibly slow. A black hole with the mass of our Sun would take longer than 10 to the 67th power years to evaporate, far longer than the current age of the universe. In 10 to the 100th power years, even supermassive black holes will evaporate completely. The universe will end as a cold soup of subatomic particles dispersed across infinite space, with occasional flashes of light from the final black hole, evaporations marking the last moments of energetic activity in cosmic history. Yet this distant future doesn't diminish the beauty and meaning of our present cosmic moment. We live in a golden age of cosmic time, when stars still shine abundantly and the universe remains vibrant with energy and possibility. Our epoch permits the emergence of life and consciousness before the final cosmic winter. In this ephemeral cosmic moment, the Milky Way shines splendidly as our home, in an immensity that simultaneously erases it and makes it precious. A paradox that defines both our galaxy and our own conscious existence within it. If you're still awake, it's because the content was really good. So take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.